So far, we've been discussing airflow through the engine, but it isn't the actual airflow we're interested in. It's actually the amount of oxygen contained in the air that's important. Air is made up of many components, and oxygen only makes up around 20%. The reason we're interested in the oxygen content is because this is the component of air that combines with the fuel during the combustion process. All things being equal, the more oxygen we have available, the more power we can produce. With this in mind, we need to know what mass of oxygen is contained in a given volume of air, and this is described by the air density. Let's talk about what the term density actually means. Just because we have a fixed volume doesn't necessarily mean that it will contain the same mass. Consider if we had two containers, and both containers measure 1 cubic foot. The first container is filled with feathers, while the second container is filled with sand. Both containers hold the same volume of material, but their weight would obviously be dramatically different. This is because the two materials simply have different densities. Air density is described by the Greek symbol ρ. The equation to calculate air density in units of pounds per cubic foot is shown here. This is P divided by R multiplied by T. Let's discuss each element in the equation separately. Rho is the air density, and this is what we're trying to calculate. P is the absolute pressure measured in pounds per square inch. R is a constant known as the specific gas constant, and in imperial units is defined as 53.35. Finally, T is the air temperature in degrees Rankine. I'll just briefly mention the Rankine scale before we move on. Similar to absolute pressure, the Rankine scale references absolute zero, which is the theoretical temperature at which all particles stop moving. This is equal to minus 460 degrees Fahrenheit, so to express temperature on the Rankine scale, we need to add 460 to the value. In this case, our standard temperature of 59 degrees Fahrenheit would become 519 on the Rankine scale. Lastly, we also need to change the units of pressure from pounds per square inch to pounds per square foot, since that's how we want to express our density. To do this, we need to multiply our pressure in PSI by 144, since there are 144 square inches in 1 square foot. If we look at our equation now, we can see that we're multiplying the pressure on the top by 144, but on the bottom of the equation, we're multiplying our temperature by 53.35. We can simplify this as 144 divided by 53.35, which is equal to 2.7. So we can just multiply the pressure on the top of the equation by 2.7 for simplicity. This accounts for the specific gas constant as well as changing the units from pounds per square inch to pounds per square foot. Now we can put some numbers into this equation and calculate the air density under the standard conditions that we've already discussed. We already know that air pressure is equal to 14.7 psi under standard conditions, and we now know that the air temperature is equal to 59 degrees Fahrenheit, which is 519 on the Rankine scale. Now we can solve the equation and we find that the air density under standard conditions is equal to 0.076 pounds per cubic foot. The key points you need to understand from this module is that air has a density and that this density varies with both temperature and pressure. Remember, it's the mass of oxygen contained in the air that we're really interested in when it comes to the performance of an engine, so we need to know how to calculate the air density based on the current operating temperature and pressure.